Hey everyone, we've all seen water freeze into ice, right? But have you ever wondered how a massive pool of molten metal turns solid? It's a fundamental process, one that builds everything from our skyscrapers to our spaceships. And today, we're going to pull back the curtain and uncover the hidden rules that make it all happen.
So let's ask the big question. What really happens when liquid metal cools and becomes solid? You might think it just freezes, but the reality is way more interesting and complex than that. And the answer all boils down to one critical question. Is the metal pure, or is it a mixture of different elements?
And right here, this is the whole game. On the left, you've got a pure metal. It freezes at one single constant temperature, forming these long, orderly columns, kind of like microscopic icicles. But on the right, you have an alloy, a mixture. It doesn't freeze all at once. It solidifies over a range of temperatures. This creates a slushy, mushy zone where these beautiful, intricate, tree-like structures called dendrites form. Think of it like tiny metallic frost patterns. This one single distinction is the key to almost everything in metallurgy.
To really understand why this happens, we kind of have to learn a new language. The language that materials scientists use to describe these incredible transformations from a liquid into a solid.
Okay, first word in our new vocabulary, phase. And it's not as scary as it sounds. A phase is just a distinct state of matter. You know this already. Think about water. You've got ice, liquid water, and steam. They're all the same chemical, H2O, right? But they look different, they act different, they are different phases. Simple as that.
So how does a new phase even begin? It all starts with a process called nucleation. This is the magic moment, the instant the very first tiny, stable, solid crystals, or nuclei, are born inside that molten liquid. It's the tiny spark that kicks off the entire solidification process.
Now, if you can imagine millions of these little crystals forming and growing inside an alloy, things can get pretty chaotic. How on earth can we possibly predict what the final structure is going to look like? Well, engineers have a secret weapon, a kind of map. And here it is, the phase diagram. Seriously, you should think of this as the weather forecast for alloys. For any given mix of metals and at any temperature, this chart tells you exactly what phases you should expect to find, solid, liquid, or a mix of both. It's one of the most powerful tools in all of engineering.
Let's break this map down. That top line you see, that's called the liquidus line. As you cool a molten alloy, the moment its temperature crosses this line, bam, the very first solid crystal forms. It's the point of no return for the liquid phase.
And if the liquidus is the starting line for freezing, this bottom line, the solidus, well, that's the finish line. Once the temperature of the alloy drops below this line, the very last drop of liquid is frozen. Everything is 100% solid.
So the crucial area for any alloy is the region between those two lines. This is that mushy zone we talked about. In this zone, you've got solid crystals just floating around in a liquid melt. It's a two-phase region where all the important transformations happen that give an alloy its final unique properties.
But check this out. The phase diagram is more than just a map. It's also a calculator. It can tell us not just what phases are present, but exactly how much of each phase exists. So if we pick a random point inside that mushy zone, how do we know if it's 10% solid or maybe 90% solid? To figure that out, we use a simple but really powerful mathematical tool called the lever rule. Now, it sounds complicated, but it works just like a seesaw. It's easy. First, you find your spot on the map, your exact alloy and temperature. Second, you draw a horizontal tie line straight across the mushy zone. And third, here's the trick. To find the percentage of solid, you take the length of the opposite lever arm, the liquid side, and you just divide it by the total length of the line. That's it.
Let's make this real. Imagine we have an alloy that's 40% metal B and 60% metal A. We cool it down to a temperature that's right in the middle of that two-phase region. So we draw our tie line and we use the lever rule.
And there it is, a precise answer. At this specific temperature and composition, the alloy is exactly 62% solid crystals and 38% liquid metal. That abstract map just gave us a concrete, quantitative result. This is how engineers can precisely predict an alloy's behavior.
And this isn't just theory for theory's sake. These phase calculations directly predict the internal microstructure of a metal. And it's that internal structure that determines its real-world properties, like its strength and its toughness.
And there is no phase diagram more important than the one for iron and carbon. This is the blueprint for all steel, the most widely used engineering material on the entire planet.
Deep within the iron-carbon diagram, something absolutely amazing happens. It's called a eutectoid reaction. And get this is a transformation that happens when the metal is already solid. One type of solid crystal, called austenite, cools down and spontaneously transforms into two completely new solid phases. It's like one kind of ice suddenly changing into two different kinds of ice all at once.
For steel, this magic moment happens at a very specific spot, exactly 723 degrees Celsius and a carbon content of 0.8%. At this precise point, solid austenite transforms into a new microstructure called pearlite. So what is pearlite? Well, it's not a single substance. If you could zoom way in, you'd see it's this incredibly fine, layered structure, like microscopic plywood. It's made of alternating plates of a soft, ductile iron phase called ferrite and a hard, brittle compound called cementite. This combination of soft and hard layers woven together is what gives steel its legendary blend of strength and toughness.
So, let's zoom out. Why does all this talk of phases and diagrams and rules, why does it actually matter in the real world?
Because by understanding and controlling these transformations, we can become architects of materials. We can design alloys to be incredibly strong for buildings, corrosion-resistant for medical implants, hard enough to cut other metals, or light and tough enough for airplane wings. Every advanced material you see around you is a product of mastering these fundamental rules of solidification.
Which leaves us with a final thought. We've learned to read this secret language of how metals freeze. By mastering these rules of composition and cooling, we've already created the materials that define our modern world. The only question left is, what seemingly impossible materials will we design next? Thanks for tuning in.